integration or antiderivatives. So the basic idea is to understand how integration is opposite to that of the derivative. If you take any function a of x, then you find derivative of this function as d by dx of a of x. So once you find the derivative of this function, you get another function, let me call it as function b of x. So the derivative of given function a of x is giving you another function called as b of x. But if you find the integration of b of x, so let's find the integration of b of x, which is given as integration of the function b of x with respect to x. So we can see that once you find the integration of b of x, we again get back to function a of x. It means if you find the derivative of function a of x, you get b of x. And if you find integration of function b of x, you come back to the a of x. It means derivatives and integration both are having opposite effects. So we can write down here that if derivative of a function a of x is b of x, then if I bring derivatives on this side, I will get a of x as integration of function b of x dx. This is a very important point to understand here, that if I perform derivative of function a of x, I get b of x. So if I bring derivatives to another side, that becomes the integration to the function b of x. Okay, I can perform various operations similarly, like derivative of a function f1x gives you f2x. So it means if I find integration of f2x, I should get f1x. That means integration of functions x to x, f2x dx will give you f1x. Okay, so this is very important. So I can say that derivatives and integration both are having opposite effects. So integration has the opposite effect to that of the derivative. Now we will see some examples on the basis of this concept, how derivatives and integration are opposite to each other. So let's see one example here, and we are interested to find the integration of x raised to n. So in order to find integration of x raised to n, I can use the concept of antiderivative. So what I will do first is, let's say derivative of a function x raised to n plus 1 divided by n plus 1 plus a constant value which is c. So let me first find out the derivative of this. So derivative of this is going to be, I will distribute the derivative, so I'll get d by dx, derivative of the first function, and then derivative will also go to constant. So distributive property it follows. So derivative of constant c. But as we know that the derivative of constant is going to be 0, this is going to be 0. So only we will have to find derivative of x raised to n plus 1 over n plus 1. Here n plus 1 is a constant. So this can be taken outside the differentiation. So I can write down here this as 1 over n plus 1 and the derivative of x raised to n plus 1. So derivative of x raised to n plus 1 will remain as it is. So here the derivative of x raised to n plus 1 is nothing but n plus 1 x raised to n plus 1 minus 1. So here this both n plus 1 in the denominator and the numerator will be cancelled out, and here 1 plus 1 will become 0, so we will get only value as x raised to n. So we got a very important outcome here is derivative of x raised to n plus 1 over n plus 1 plus c is x raised to n. Now by knowing the property that derivative is the opposite of integration, or integration is the opposite to derivative, so if I bring this derivative sign over here, that will become integration. So by knowing that the integration is nothing but antiderivative, so if I bring derivative on this side, you will get x raised to n plus 1 divided by n plus 1 plus some constant c is nothing but, when this derivative d by dx goes on other side over here, it becomes integration. So now I can write down that here. So it is nothing but integration of x raised to n dx. So I got a very simple outcome that the integration of x raised to n dx is x raised to n plus 1 over n plus 1. So we got that integration of x raised to n dx is x raised to n plus 1 divided by n plus 1 plus a constant value c. Similarly, we can take another example here. We can find the integration of 1 dx. We know that the derivatives of a term which contains only x plus I can always add a c, because derivative of any constant function does not make any difference, so I can always add a c over here. So derivative of x plus c is going to be derivative of x plus derivative of c, but derivative of c is 0, as we know that this is going to be 0, and derivative of x is going to be 1, so I can write down here the derivative of x plus c is nothing but derivative of x is going to be 1. So as per rule, integration is antiderivative. It means if I take this dy dx and if I bring it on this side, this is going to become integration of this function. So I can write down here that x plus c is nothing but the integration of 1 with respect to x, that is 1 dx. So that is why integration of 1 dx is nothing but x plus c. So we have got here integration of 1 dx is x plus c. Similarly, let's see another example. We want to find the integration of sine x with respect to x. Okay, so now we know that the derivative of, if I take differentiation or derivative of function minus cos x plus c. So we know that by our basic understanding of differentiation, so we can write down this as minus derivatives of cos x and then plus derivative of c, that is a constant function, but the derivative of constant is going to be 0, and derivative of cos x is minus sin x. So you will be getting from here derivatives of minus cos x plus c equal to, now it is minus, and derivative of cos x is minus sin x. So this will give you the derivatives of minus cos x plus c equal to sin x. Now as per the definition of integration, it is antiderivatives, it is opposite to the derivative. So if you bring this derivative from here to here, this will become integration. So you shall be getting integration of sin x dx as minus cos x plus c. So we got integration of sin x dx as minus cos x plus c. So let's see another example here. We want to find the integration of cos x dx. So to find the integration of cos x, we shall be using derivative of sin x. Okay, so let's see derivative of sin x. So sin x, and we can always as a constant, because the derivative of constant is 0. So this is going to look like derivative of sin x plus derivative of constant c. So if you simplify this, you will be getting derivative of sin x is going to be cos x, and derivative of constant is going to be c. So you get derivative of sin x plus c is going to be cos x plus 0. Now if I bring this derivative from left hand side to right hand side and apply on this cos x, it will become integration. So you will get from here that sin x plus c is nothing but the integration of cos x with respect to x, like this. So we can write down finally the integration of cos x is sin x plus c. So one more example, let's see. We have to find the integration of secant square x. So we know that the derivative of tan x is secant square x. So let's write down that. So we know the derivative of tan x. So derivative of tan x, I can always add a constant here, because derivative is going to be 0. So derivative of tan x plus c is nothing but derivatives of tan x plus derivative of constant c, and then derivative of constant is 0, and derivative of tan x is sec square x, so we can write down here. Therefore you'll get derivative of tan x plus c equals secant square x. And now if I bring this derivative from left to right, because derivative is opposite to the integration, so it will become integration over here. So you'll be getting tan x plus c is nothing but the integration of secant square x with respect to x. So now we can write down that the integration of secant square x with respect to x is tan x plus c. Let's see one more example here. Similarly, we can write down for integration of cosec square x. We know that the derivative of cot x is minus cosec square x, so I'll be using derivative of minus cot x plus c, and that is going to be derivative of minus cot will be minus, and the derivative of cot is minus cosec square x, and derivative of constant is 0, so you'll be getting derivative of minus cot x plus c as cosec square x, and if I bring this derivative from left to right, this is going to become an integration of the right function, this function, so we'll get minus cot x plus c is the integration of cosec square x dx. So I can write down directly that the integration of cosec square x dx is minus cot x plus c. You can also see some more examples. Here we wanted to find out the integration of sec x tan x. So we know that the differentiation of secant of x plus c is nothing but, if I differentiate secant of x, I'll get secant of x into tangent of x, and the derivative of c is going to be 0. So if I bring this derivative from left to right, you'll be getting secant of x plus c. So this derivative, if you bring from left to right, becomes integration. So integration secant of x tangent of x with respect to dx. Okay, so we can write down from here that integration of secant of x tangent of x dx is nothing but secant of x plus c. So that's a simple derivation we got. Next example. So we can similarly do for cosecant x into cot x. So we know that the differentiation of minus cosecant x plus c is going to be minus, and the derivative of cosecant is nothing but minus cosecant into cot x, and the derivative of c is going to be 0 because of constant. So you'll be getting from here derivative of minus cosecant x plus c equal to cosecant x times cot x. Now if you bring this derivative from left to right, because derivative is opposite to the integration, so this will become integration. So you'll be getting from here that minus cosecant x plus c will be nothing but the integration of cosecant x into cot x dx. Okay, so integration of cosecant x cot x. So that is simple. So we can say that the integration of cosecant x cot x is nothing but minus cosecant x plus c. Let's look at some more examples. We have to find the integration of 1 upon 1 plus x square, derivative of tan inverse of x. The derivative of tan inverse of x is 1 upon 1 plus x square. So I am going to take derivative of tan inverse of x and c. C I can always take because there may be some constant whose derivative becomes 0, right? So it is always advisable to take a constant. So tan inverse of x plus c, and derivative of tan inverse of x is going to be 1 upon 1 plus x square. So you'll be getting derivative of tan inverse of plus c is nothing but 1 divided by 1 plus x square. Now as far as rule is, if I bring derivative from left side to right hand side, this is going to become integration to this function. So I will be getting like this: tan inverse of x plus c is going to be integration of 1 divided by 1 plus x square. That's what we got. So integration of 1 divided by 1 plus x square is nothing but tan inverse of x plus c. Similarly, we can take minus 1 upon 1 plus x. So we know the derivative of cot inverse of x plus c is nothing but minus 1 upon 1 plus x square. Derivative of c is going to be 0. So if I bring derivative from here to here, I'll get integration. So therefore, we'll be getting integration of minus 1 over 1 plus x square dx will be nothing but cot inverse of x plus c. Okay, so this is the integration of minus 1 over 1 plus x square is nothing but cot inverse of x plus c. Now we have another example to find integration of 1 over under root of 1 minus x square. So we know that the derivatives of sine inverse of x, plus c is nothing but 1 divided by 1 minus x square. Now derivative of c is going to be 0. So if I bring this derivative on this side, that will become integration. So I can write down the integration of 1 divided by 1 minus x square. Integration of 1 divided by 1 minus x square is going to be sine inverse of x plus c. So which is we have got here. Similarly, we can find out the integration of minus 1 upon 1 minus x square. So we know that the derivatives of cos inverse of x plus c is nothing but minus 1 over under root of 1 minus x square, because derivative of constant is going to be 0. So if I bring derivative on other side, that will become integration. So I can write down straight away integration of minus 1 over 1 minus x square dx equals cos inverse of x plus c. So now let's see another example. We would like to find the integration of 1 over x under root x square minus 1. So that's again very simple. We know that the differentiation of secant inverse of x plus c is going to be, differentiation of secant square is nothing but 1 over x under root x square minus 1, and the derivative of constant is going to be 0. So if I bring derivative from left to right, that becomes integration. So we can straight away write down integration of 1 over x under root of x square minus 1 dx is going to be same as secant inverse of x. So we have got here integration of x under root of x square minus 1 is secant square of x minus 1. So let's see the next example here. So here we have to find the integration of minus 1 over x under root of x square minus 1. We know that derivatives of cosecant inverse x plus c is minus 1 over x root of x square minus 1, and the derivative of c is going to be 0. So if you bring derivative on next side, that becomes integration. So we can straight away write down the integration of minus 1 over x square minus 1 dx will be cosecant inverse x plus c, which is the result we have got here. Now let's see the next example here. Now we know that the differentiation of log of x. So if you take derivative of logarithmic function x plus c, so as per the rule of differentiation, we know the derivative of log function is 1 over x and derivative of c is going to be 0. So if I bring derivative on next side, I'll be getting from here that the integration of 1 over x dx equals logarithmic function of x plus c. So this is how we can find out the integration of 1 over x dx is ln x plus c. Next example, let's see. We know that we have to find the integration of e raised to x dx. So we know that the differentiation of exponential function e raised to x plus a constant is nothing but, if you differentiate e raised to x, the value is going to be same, e raised to x, and the derivative of c is going to be 0. And if I bring this differentiation on next side, because differentiation is nothing but anti-integration, or it is opposite to the integration, so here it becomes integration, so here it becomes integration. So we can write down that the e raised to x plus c is integration of e raised to x dx. So we can directly write down that the integration of e raised to x dx is e raised to x plus c. That is what we have got here as a result, integration of e raised to x as e raised to x plus c. So similarly, if you want to find integration of a raised to x, so we know that if I take derivative of a raised to x divided by logarithmic function ln a plus c. So its ln a is constant actually, so a raised to x by ln a, that is log a, natural log a. So that is going to be, now we'll differentiate this, so differentiation of a raised to x divided by natural log a plus differentiation of constant c. But the differentiation of constant c is going to be 0, and here the derivative of a raised to x. So now here, if you want to find the derivative of a raised to x, this natural log of a is constant, I can take it outside. So it is 1 over natural log of a, and the derivative of a raised to x is nothing but a raised to x natural log of a. So this natural log of a in the numerator and denominator will be cancelled out. So we'll be getting, therefore we can get derivatives of a raised to x divided by natural log of a plus a constant is nothing but a raised to x. So by rule, if you take derivatives on next side, that becomes integration. So you can directly get from here that the integration of a raised to x dx equal to a raised to x divided by natural log a plus c. So this is what we got, is the integration of a raised to x dx, and that is what we have got in the result also. Integration of a raised to x dx is a raised to x natural log a plus c. Now we would like to compile all the derivatives and the integration we got so far. So in the left hand side we will be writing the differentiation, and then in the right hand side we will be writing the integration of those functions. So for example, derivative of x raised to n divided by n plus 1 is x raised to n. So the integration of, so that will give you the integration of x raised to n as x raised to n divided by n plus 1. Similarly, the next function, the derivatives of x is 1. So you'll get integration of 1 as x here. Derivative of sin x is cos x. So we can say the integration of cos x is sin x. We also have derivative of cos x is minus sin x. So integration of sin x is going to be minus cos x. That we have here, integration of sin x is minus cos x. Derivative of tan x is sec square x. So you will get integration of secant square x as what? Derivative of tan x is secant square x. So we can get the integration of secant square x as what? Tan x. That is here. Derivative of cotangent x as minus cosecant square x. So we can say the integration of cosecant square x will be the cotangent of x, cot x plus c. Now similarly we can have the functions like tan inverse of x. Derivative of tan inverse of x is 1 upon 1 plus x square. Therefore integration of 1 upon 1 plus x square is tan inverse of x. Similarly for cot inverse x we'll have, now sin inverse x, derivative of sin inverse of x is 1 upon 1 minus x square. So integration of 1 upon 1 minus x square is sin inverse of x. Similarly for cos inverse x we can write down the derivative of secant square x is 1 upon x, 1 over x divided by x under root x square minus 1. So integration of 1 over x under root x square minus 1 is secant inverse of x. Similarly we can write down for cosecant inverse x. We also have two more functions, which is derivative of e raised to x is e raised to x. So integration of e raised to x will be same as e raised to x. Derivative of a raised to x divided by natural log of a is a raised to x. Therefore, integration of a raised to x as a raised to x divided by natural log of a plus c. Okay, so this here we have discussed about how the integration and derivatives are opposite, and by using same concept we have found some standard results for integration. Thank you very much.